So it's my pleasure to welcome you. Yes, thank you for coming down from London. So I'm probably not going to get this right. Jie
Zhang,
is working at King's College, as it also already says on the slides, but has a background of working at UCL before, and consultant at Meta. And you're working on mutation for assessing, improving AI systems. I'm very much looking forward to find out what that's all about.
Yeah.
So without any ado, it's up to you.
Yeah, thanks a lot for the introduction. So hello everyone, hello the people online. I actually have a bit more slides about myself.
Oh, that's good.
Yeah. So my full name is Jie M. Zhang. So I have a middle name which represents my English name, Marina. I have this because my full name Jie Zhang is too popular in China, and there are more than 250,000 Jie Zhangs in China. So I have to add a middle name to let people find me when they try to Google my name. Anyway, so I work at the intersection between software engineering and AI, and there are two directions: software engineering for AI and AI for software engineering. I work on both directions, and now it's actually more like a loop, with large language models for code generation for all different software engineering tasks. It's more like a loop, and I work a lot on trustworthiness of software and also AI. For software, we have software testing to try to find bugs. So I worked on metamorphic testing, regression testing, and also mutation testing, which is related to the topic that I'm going to introduce today. And for AI trustworthiness, I work a lot on the fairness of machine learning classifiers, and also on different other systems like machine translation system and code translation systems. And so nowadays, everyone is working on LMs. I don't know what's the situation for you and for Sussex AI group.
We have a couple of people who do something with LLMs.
Yeah.
Very many actually.
Yeah. So in our community, we're all in LMs.
Yes.
So I'm also working on LMs for code, and some of my current ongoing work are agent-based code generation. We let different agents collaborate with each other to generate code, and also benchmarking and also improving the efficiency and fairness of the code generated by LMs, and also using LMs for different tasks such as fault localization and also program repair. So I got my PhD from Peking University in 2018, and then I was also a research intern at Microsoft Research Asia. And then after my PhD, I went to UCL to do a postdoc for almost 4 years, I think. Then I joined King's College London 2 years ago. So this is, did you visit King's before?
I haven't actually personally, no.
But welcome to.
Used to work at King's, so
yeah. So welcome to visit King's when you have time. And this is the Department of Informatics. It's located in Bush House. It was previously the headquarters of BBC. So now it's a part of King's. And our department has 3 floors, I think, in this building. And we have a very nice view of the building. And this is a photo that I took on top of the building. Very great location. You can see those sightseeing places like Big Ben and London Eye. Yeah, actually, I could see London Eye from my office windows, which is really nice. So the department, we have more than 85 academic staff. So it's expanding. It's still expanding. I think the target is 90 something. It's almost reached the target. And there are more than 150 PhD students with almost 1,000 undergraduate and master students. So I think it's a relatively large department. So I have different research groups. So on the left side, you can see the names of these research groups, including cybersecurity, algorithm data analysis, and AI, and human-centered computing, and software system is the group that I belong to. And we also have different research hubs covering different topics such as arts and finance, health, security, sustainability, and so on. Yeah. So the topic that I'm going to introduce today is mutation for AI, which is closely related to a testing technique in software engineering called traditional mutation testing. And have you heard of it? If you have, you
This
can,
no, I don't actually know. So if you could explain
yeah.
what it is, that would
Yeah.
be great. Yeah.
Yeah. So what about the online participants? If anyone have heard this term, you can probably hands off.
I don't see hands.
Yeah.
Yeah, but
Yeah.
okay.
I'll just explain a little bit. I don't know whether you watched this movie. It's called Who Watches the Watchmen? So they ask a very interesting question. The movie's name is actually called Watchmen. And then they ask this very interesting question, who watches the Watchmen? So in software testing, we have a similar problem. We have test cases. The goal of test cases are to find bugs, right? But how do we know that these test cases are strong enough to find bugs? So the equal question here is like, what tests the tests? And the answer is mutation testing. So we have the original program and the test, and then we apply some changes to the original program. We inject faults in this program. And every time we inject faults, we create a mutant. So all these programs with injected faults are called mutants. And how we generate these mutants, we based on mutators, or we call them mutation operators. So there are some human heuristic rules. For example, we change plus to minus, we change equal to smaller than, something like that. And then, the mutant is like the program with the simulated fault, right? Then we can check whether the test suite is able to detect those simulated faults. If they could, we think the test suites are okay. Otherwise, they couldn't find the simulated faults, then they need improvement, right? So that's the idea. So if they could find this simulated fault, we see that this fault or this mutant is killed. Otherwise, we see that it's alive. So if we ask the three big questions, where do we do the mutation? We mutate the source code, right? And how do we do the mutation? It's based on human heuristics, like those rules, like plus to minus and so on. And it's called mutation operators. Why do we do the mutation? We aim to evaluate the test cases. But after my PhD, I realized that mutants, they're actually much more powerful than just doing test assessment. And I start exploring their power beyond test assessment. So that's the content of my talk today. I believe that they are powerful because I think they bring changes. So you can think mutations, they are brought by making changes, and while making changes, we really can do a lot of things. Can skip this one. So in this talk, I will introduce how I apply mutation for improving AI systems, including testing and improving machine translations, and also validating machine learning classifiers, and benchmarking and improving AI fairness. Yeah, so the first work is mutational testing and improving machine translation. And it's a work published by top-tier software engineering conferences. Maybe you haven't heard of them, XII, International Conference on Software Engineering. So it's published, published at XII 2022 and 2020. So the problem, of machine translators like Google Translate, I don't know how often you use Google Translate, but for me, because I'm a non-native speaker, I actually use them a lot. They're not perfect. They have lots and lots of issues. And in this slide, you can see some very interesting translation issues. So the left image, it's a Chinese menu, and the Chinese characters actually says the dish is roasted gluten, but the English translation is roasted husband. So apparently the designer of this menu over-trusted the machine translator that they used, right? And just, blindly put the English translation here. And on the right, it's a sign, and the Chinese says, watch your step, but the English translation is sleep and fall down carefully. These are like a translation disasters that are caused by the problems in machine translators. So how should we improve these issues? Oh, actually, there is another example. So sometimes these machine translations, they have fairness issues too. And these are real examples that I found from Google Translate several years ago, and Google Translate has now fixed them, but it's easily to find other similar issues too. So the problem is that when I ask Google Translate to translate English to Chinese, when I say men do good research in computer science, good is translated into very good in Chinese. But when it's women, good is just a lot. So it's the same for male students and female students. If it's male students, good is very good. If it's female students, good is a lot. And apparently, very good and a lot are obviously different, right? So as a female researcher, I feel quite complex seeing results like this. So how should we handle these kind of issues? We can think about the AI community. The traditional ways to do this is, first we need to detect the issues, right? So it's usually rely on, they may find some humans to label the translations to check whether they're correct or wrong, or they rely on human users to report the incorrect translations. And once they have found the issue, they may debug the training data, add more training data, or they optimize their learning algorithm, retrain the model. So the whole point is to retrain the model, produce a new model, and then this model hopefully would repair some of the detected translation issues, right? So on this method, they have lots of issues. It's very expensive because they need human or provided oracle. And I think there was a statistic saying that one person labeling one image costs more than $5. So that's the cost of labeling. And and also you need to collect more data and train the model. So it all takes money and also time, right? So it's not online, it's not real-time fix because model training takes a lot of time. And after you produce the new model, the users already use the horrible translations in their daily lives. So there is a delay between the detection and the fix. And also it's not bug specific because it's difficult to control the model retraining procedure. If you have found some translation issues, you try to fix them. You retrain the model, try to fix these kinds of issues, but other new issues may appear, right? So it's not bug specific, and other well-formed translations might be affected for the new trained model. So those are the issues of traditional ways, and so we think, okay, we hope to bring some other ways to complement these issues of traditional approaches. And that's the idea of mutation for testing and also improving translation issues. And the idea is that we use a mutation to generate lots of input sentences. And in this way, we check whether the translation provides consistent translation for these input sentences. For example, I would mutate the men to women, apples to oranges. So these, we call them context similar words. And then the idea is that the non-mutated part, they are supposed to have consistent translations. If the translation is not consistent, then we think at least one of them is problematic. So that's the idea of testing. And we also want to repair these translation issues in real time so that users can just get fixed translations immediately and they won't even realize that. So what we do, of course, we do this without human oracle. We can't just let a human standing by saying that this translation is correct or wrong, right? We want to do this completely automatically. So what we do is that we generate more mutants. For example, in this example, we mutate female to male, and then students to teachers, and good to great. So all these different mutations. So each mutation, they would have a translation. And then we would rank these translations because they bring changes to the input sentences. And then we check maybe the translator is doing good for some of these mutants. So we rank these translations. We rank them either based on predicted probability or majority voting so that we know, okay, actually, for one mutant, the translation is better, so we know a better translation. But this translation is for the mutant, not for the original sentence, right? So what we do is that according to the rule that we get this mutant and the original translation, we map back to the translation of the original sentence. In this way, we kind of put a patch into the original translation to fix the translation issue.
Sorry, can I ask, so but the ranking,
yeah,
I didn't fully understand what your criteria are. Is it the translation that happens the most often that is ranked highest? Or how do you decide what the best translation might be in this ranking?
Yeah, so the challenge here is that we want to estimate which one is better because we don't have human oracles. We just want to guess, right? So our strategy is to either use majority voting. So the one that has the largest similarity with the remaining, we think that's the better one. Yeah. Or predictive probability, because the machine translator would have a predictive probability. We can decide. Yeah, the confidence thing. So we can use that to rank the translations too. Yeah. So the results shows that the testing results we show that Google Translate, the most widely used machine translator, it has more than 1/3 inconsistent translations on the data set we use, and also for the repair part, we found that our repair approach could repair 50% of these translation issues that we detected. And on our own machine, we found that it's very efficient. For example, for bug repair, it costs less than 2 seconds. But we think that for big companies like Google with their machines, it's going to be much, much faster. So this approach is, compared to the model retraining approach, it's you can think that it's a black or white box because we don't need the training data, we don't need the algorithm, right? We just design test inputs and post-process the translations, and it's really cheap and very fast. It's real-time fixing, and it's flexible because we only target those translations with issues. We don't touch those well-formed translations, not like model retraining. So again, ask a 3 question for this approach. Where did we do the mutation? We mute the model inputs, like the input sentences for the machine translator, and model outputs, which is the translations of the sentences, right? And we replace the context similar word, like apples to oranges. So why do we do the mutations? Because we want to test and improve the machine translation systems. The second one is more related to AI. I guess it's mutation for validating machine learning classifiers, and it's a work published at Neurocomputing. And when it's a work done when I was a postdoc at UCL, and with my postdoc supervisor Mark Hummel, and also John Taylor, who used to be the head of department of computer science at UCL. So we use machine learning models a lot, and the issue is how should we validate those machine learning models? And there are 2 branches. One is applied machine learning. For example, we usually use auto-sample validation, right? Either cross-validation or test accuracy, test set. The other branch is statistical machine learning, like VCD dimension and random complexity. So all these branches, they have limitations. For example, applied machine learning, the auto-sample validation, there is a possibility that the test that it's insufficient, and also because usually it's you really mix all the data together. You extract a part of the data as the test data, so it usually has similar bias as in the training data, right? And also, lots of people use the similar data sets, then it causes overfitting to test data, and another issue is that it does not reflect after distribution generalization, right? And for statistical machine learning, obviously, it's very difficult to compute in practice, and it provides only bounds that can be quite loose. So those are the limitations. So I was thinking whether we can do things in a different way and to not replace these conventional methods, but again, to complement them and to address some of the limitations. That's the idea of mutation validation. The idea is actually quite straightforward, quite simple. So imagine that we are teaching this baby to learn what is a cat and what is a dog. So give the baby a bunch of cards. So we say, okay, first one is cat, second one is dog, and then dog, cat, dog. And for the last one, we change the label deliberately. We say that it's a dog. And then in the second round, we give these cards to the baby and ask what animals these images represent. And so if the baby really learns what is a cat, what is a dog, so when we ask what the final animal is, the baby would be able to say that it's not a dog, it's a cat, right? So this smart baby is not biased by the incorrect label in the first round. So we can think that the first round is the training data. And then after we gave these cards to the baby was like secretly building the training model in their brain. And then in the second round, checking the training accuracy of this model. So a good learner is supposed to, not to be biased by the incorrect labels in the training data. So that's the idea. It's quite simple and straightforward. So I think that a good learner, if the learner truly learn the patterns in the data, it would be less likely to be fooled by a small ratio of incorrect labels. It has to be a small ratio. If it's like too much, if it's over 50%, then obviously the learner would have to learn the noisy labels instead of the true data distribution. But for over complex learner, it has extra capacity to fit incorrect labels. So they may, so they would just memorize the incorrect labels and still predict the incorrect labels in the second round. Yeah. And for very simple learner, because it has very poor learnability, they would have low training accuracy with and without the incorrect labels. So in this way, we could just check the training accuracy difference before and after the labels. And we produce metric inspired by the statistical machine learning. Remember that we have the original training data. We have the model trained based on the original data. We also have the mutated training data with the changed labels. We also have the model retrained based on these incorrect labels. And then this metric is calculated, based on the training accuracy of the original model on the original training data, and also the model trained on the mutated training data and the training accuracy on this mutated training data. So we check their difference, and we also check the model trained on the mutated data on the original training set. So we use this calculation, and this one is the noise degree, which means the ratio of labels that we change. So for this one, you can imagine that for a very good learner, if it's less biased by the incorrect labels, then the model trained on the mutated training data would be very similar to the original model because it's not biased by the incorrect labels. So they would be similar, then this one is going to be large. So that's the model training accuracy on the original training data, right? And this one is going to be small because their difference would be small. And then this, and the metric value would be large. So a better learner has a larger model validation results. Yeah. Ideally, this training accuracy is 1. And this one, the difference it actually equals to the noise degree, which is the ratio of noisy labels, because the learner just detects all the incorrect labels. And then the M would equals to 1. So in the ideal case, for a perfect learner, M equals to 1. So how do we do the evaluation? How do we know that this metric performs better than test accuracy and cross-validation? It's actually quite tricky, and we thought about several strategies. The first one is that we can check the match between data patterns and the decision boundaries of a classifier. So you can see that these are some static data, and you can see the data patterns. For example, the first row is the moon shape, the second row is the circle shape, and then inside each cell, the M value represents the metric that the model validation provides. Hello. Hello. And then CV represents cross-validation, and test represents test accuracy. And so you can for example, let's look at the example in this line, the decision tree in the middle one. If the people online can see my mouse, this one? Yeah. Great. So if we focus on decision tree, if we look at the circle distribution, the decision boundary provided by the decision tree is a square, which is really different from the data distribution, right? But still, test accuracy, it's perfect. It's 100%. And it's the same for cross-validation, but our metric mutation validation says it's not perfect. It needs, here. It's not perfect. It needs some improvement. And then for the naive bias, it says it's a perfect classifier. Yeah. And another ground truth that we think we can check is for the SVM classifier. And we know that there are two parameters, C and gamma. And really, if you check those machine learning tutorials, they would tell you that a good model is expected to be found close to the diagonal, so which is around here. But if you check cross-validation or test accuracy, you can see that when C and gamma are very large, like this area, the test accuracy or cross-validation results are also almost perfect, which means that they couldn't provide a signal that C and gamma are overly large, so for over complex models. So, but for mutation validation, we can see that these areas, they are red, which means that the metric values are low. So Emily thinks that the parameters in this area are not good enough, and we'd better find parameters in this area, so which is more accurate than cross-validation. So to summarize this work, there are more results in the paper, and I won't introduce them in details, but to summarize our findings is that we found that the Emily metric captures well the degree of match between decision boundaries and data patterns in model selection. And also it helps to find a simpler model with comparative performance. And it's more responsive to different hyperparameters, which means that it would help developers to tune the hyperparameters more quickly. And the last two actually are very important nowadays because we think a lot about green and sustainable AI. We want to really not overuse the more complex models and try to keep the models simpler to save energy and cost. So for this work, where did we do the mutation? We muted the training data, and we just changed the training labels to the incorrect ones, and for the purpose of validating machine learning classifiers. The next one is mutation for benchmarking AI fairness performance trade-off. And can I ask if any of you know the fairness performance trade-off in machine learning classifiers?
I think so.
Yeah, I'll introduce a little bit. So it's a work published at FSE, also a top-tier conference in 2021. And for machine learning fairness, we have protected attributes of humans, for example, race, sex, and age, right? And then these protected attributes would classify different people into different groups, privileged group and unprivileged group. So unprivileged groups are usually those groups that are at disadvantage from history. For example, for women, when we predict the salary for women, then women belongs to the unprivileged group. And the definition of fairness, actually here we're talking about group fairness regarding different protected attributes, right? So definition of fairness is that different groups, they are treated equally by the machine learning classifier when the classifier tries to make a decision. For example, when the machine learning classifier tries to predict the income of the different people, we think that the accuracy for men and women should be equal. So that's the definition. And there is really a trade-off between accuracy and fairness, which means that when we want to improve the fairness, the accuracy is really affected. So you try to improve fairness, but accuracy would decrease. That's the trade-off. And now comes the interesting question. When we try to compare different fairness improvement methods, how should we compare them? Because, some they get more fairness, they improve more fairness, but the accuracy decrease more, right? So it's kind of difficult to compare their effectiveness. And another big issue is that there is no baseline to rule out naive bias mitigation methods. So for naive bias mitigation, what I mean is that you can actually just just to trade fairness for accuracy. For example, somebody may say, I come up with the perfect fairness improvement method, then the random guess classifier. Because it's random guessing, then for different groups, the accuracy, they're equal, right?
Yeah.
They're equally worse. So it's perfect fairness, but it's basically just trading accuracy for fairness. And those are like naive bias mitigation method, and there is no way to rule out them, right? So the idea of this approach is that where we can mutate a classifier to simulate this kind of naive methods so that we provide a baseline, a benchmark for existing bias mitigation methods. Because it's difficult to train the naive model at different degrees of naivety, I would say. So we just mutate the predictions of the model. For example, previously it's 1, then we mutate the 1 to 0. In this way, we are simulating that this model is just doing a stupid thing in the prediction, in just trading accuracy for fairness. Yeah. And then we have different degrees of mutating the labels, different ratios of labels that are mutated. And then each ratio would produce a point in the left figure, because the x-axis is bias and the horizontal one is accuracy, so that you could get different plots in this figure. And if you connect them, you get a line, which is the baseline. And based on this baseline, we can classify the fairness improvement methods into different regions. And we have the win-win region, which means that both accuracy and fairness are improved. We have lose-lose region, which means both are decreased. We have the good trade-off region, which means that there is a trade-off, but the trade-off is better than our baseline. And we also have the poor trade-off region, which means that it's worse than our baseline. And based on this baseline and benchmark, we did a large-scale study of existing fairness improvement classifiers, and we found very interesting results showing that more than 50% of the existing bias mitigation methods, they have very poor mitigation effectiveness. And 15 of them, the performance is even worse than our naive baseline, which is quite interesting finding. So for this work, we mutate the model outputs that are the predictions, right? Why did we do the mutation? Because we want to benchmark machine learning performance and fairness trade-offs. Do you have any questions so far?
Yeah, I mean, if you want, I have a question about the validation approach.
Yeah, the previous one, right? The previous
one, yeah. So I was wondering, I mean, this is obviously a massive problem. I've seen so many papers using the same test set.
Yeah.
And then improving incrementally, and it becomes statistically completely insignificant at some point.
Yeah, that's true.
Now, if you auto heal method instead, and use that repeatedly, do you run into the same potential issue of overfitting? I mean, now it's not the test set, but overfitting on the method and actually not being able to discern the different methods anymore either.
Yeah, I think indeed that issue exists. It's a good question, by the way, but I assume that it should be better than test accuracy because you're changing the labels, and then you have different ways of changing labels. You also can choose different data sets to mutate the labels. So it's like a more diverse space to explore than the test set. For test set, it's, usually the test set is fixed. People just work on that test set. And then it's also an alternative way, right, other than the test set. So I would say, yeah, it's indeed the issue still exists as long as we have something to calculate a metric. Then.
And do you think that I mean, maybe that's in your paper, but do you have a measure of how well this predicts? Maybe this is okay. I'll ask the question and then we can discuss whether it's a good question or not. What does it predict performance on something new? And ultimately, these systems are built and you do cross-validation, maybe a test set to then prove that it will work on new data. Like that it make a product and it would work on new data.
Yeah.
How much does your metric actually predict how well it's going to do in the real world?
Yeah, it's a really great question, and I would say that to do that experiment, we really need the collaboration with the industry and at real cases for those unseen data, and even with distribution shift, right? Yeah, but we didn't do that in the experiment. Yeah, but we should do indeed.
But you could systematically try different models to see how your metric is doing, and then try the new data and see how they are doing and correlate these two observations. Right? That's how you go about it.
Yeah, the issue for currently, when people really have holdout sets, but even for the holdout sets, we won't say that's the ground truth because it may have similar issues with test set. Yeah, so we don't use the holdout set as the ground truth to check whether M performs better or not.
Yeah, and I almost stopped asking the question because I know it's very contentious and you can't. This whole area is so problematic in terms of if you have a product and you apply it to something, then you could argue the new data is actually out of distribution.
That's true.
Or you can say, no, that is what I wanted to build, and that within distribution, but then you have limited information you're trying. So there's actually, I don't think there's any clear answers in this space also. Yeah.
Yeah. I wonder if there are any existing benchmarks for that, like provided by the industry, for example, so that academics can really check.
Not there, but I think this is something that
very important.
We need to think about.
Yeah.
Because if you do applications, there will be disappointment at times. It doesn't perform as well as expected.
Yeah. Yeah.
So yeah. There was a very recent talk at ICLM, I think.
ICML.
ICMR. Machine.
ICLR.
ICMLR. The Machine Learning Research Conference. They had to talk about a paper that's now a bit older already, but it was called the reusable test set. And they had a slightly different approach to the same question, where they were using differential privacy to not reveal the actual test set when you're using it. They were arguing that they use it several times without polluting your overfitting your test set, which is a complementary approach, I guess, to use.
Yeah, that's a very interesting angle for solving the issue. But overall, the issue is now becoming more serious with large language models because the test set may appear in the training data of those large language models. Then when we evaluate the outcome of large language models, then the data leakage issue, right? Yeah, so I guess overall the validation issue is a big problem.
It's a life issue. Thanks. Yeah. Online questions?
Can I ask?
So
yeah, go ahead, please.
Your second paper regarding the clans, the groups, are they just a combination of the label and the sensitive attribute?
Yeah. You see, your question is.
So you have these groups, the groups.
Yes.
What are they? They just the label and the
so
attribute tied together.
The protected attributes are features.
Sorry?
The protected attributes, they are features of the data. Yeah. What we mutated are not the protected attributes, but the predictions of different people. For example, if previously it predicts that women's outcome is lower than some threshold, then we would change the prediction. But the following work, I think it's mutating the sensitive attributes, protected attributes. This one. Yeah. So maybe I just continue.
Oh, sure.
Yeah. So this one is also about AI fairness. And I'm sure we are all familiar with the ensemble methods. And in traditional machine learning, for the ensemble, we get different training data subset from the training data. And for each subset, we get a model trained on this subset. In this way, we get different models, we ensemble the results together to get the final prediction. So examples are random forests, right? And For the fairness literature, there are also some ensemble techniques, but they combine different fairness improvement methods to improve fairness. For example, they train a classifier to see when to use which fairness classifier. This is their way of ensemble. But this work, we work on a different ensemble problem. We would mutate the training data, and each time we mutate the training data, we get a new training data, and this new training data would produce a new model, and then we ensemble these models and with the original model to make the final prediction. So it's a completely new way of ensembling, but we would still call them ensembling. And we are able to do this ensemble because we use mutation to mutate the training data. So it's kind of similar to synthetic data. I just attended a seminar called Seminar in Montreal last week, and there is this fantastic talk on privacy. So they're talking that synthetic data actually plays a great role in addressing privacy issues. So in this work, I guess it's also playing a great role in addressing fairness issues. So this work is published at FSE this year. It's in Brazil. It's done by my PhD student in Seoul. And he's still a first-year student, so he has already got a first top-tier paper. The idea is, again, straightforward. You have the original data set, you have protected attributes and predictions, and this training data can be biased because due to various reasons, when we collect the training data, maybe we're not collecting the data in a professional way, and then the data is seriously biased and not evenly distributed across different groups, right? So what we do is that we mutate the protected attributes to the other side. For example, previously it's women, we would mutate it to men. It's dark colored, then we would mutate it to non-dark colored. So we change the protected one to a non-protected one. In this way, we produce a new training data. And this training data, the protected attributes are completely different with the original data. And then we produce a new model based on this mutated training data and ensemble the predictions. And we could ensemble in different ways. For example, we could just calculate the average probability to make the final prediction, or we can think about the context, the specific data instance, for example, which protected attribute it is, and also some other attributes to choose which prediction we want to use when we do the ensembling. Yeah, that's the idea. It's quite simple, but it works surprisingly well. And for example, if you still remember the baseline that I introduced, the trade-off baseline, we showed that this approach achieves the largest ratio of win-win situation, which means that more than 40% of the cases, we could improve both accuracy and fairness, and also the largest ratio of a good trade-off. And also it works well on different algorithms and tasks, including the DNN and different data sets. So it's like a university, not university. I mean, it's a scalability is very good on different methods.
So what's the number in this table?
I think
it says 99% or something. It's an accuracy,
yeah, that's a good question.
Okay.
Yeah, let me try to recall. I think it's the ratio. This one is the trade-off results. It's the ratio of the tasks that are win-win cases and good trade-off cases.
Oh, okay.
Yeah. And then this one is the changes on accuracy and fairness separately. If we want to check, for example, the changes of fairness and the improvement the changes in the performance. So these are the changes, and we can see that our approach reduces the most bias, but decreases the least performance. Yeah. So for this work, we mutate the training data the protected attributes, which are the features of the data, and we just flip the sensitive attributes for the purpose of improving machine learning fairness. Yeah, that's it. So I introduced how I explored mutation for improving AI systems, including the machine translation systems, machine learning classifiers, and AI fairness issues. So I don't know whether you have read this book, A Brief History of Tomorrow. No, it's actually the author. It's just the author of *Sapiens*. I'm sure you know *Sapiens*, right? And in the interview, he said we are in the process of becoming gods, because lots of people were discussing what's our future, what's our future with the large language models, and then his opinion is that we are in the process of becoming gods with the help of AI and large language models, obviously. But I believe that mutation would also contribute a lot to this procedure. So in future, when we think about what we mutate, maybe we are mutating our brain. But it's, he said the big question is what to do with our new godlike powers. Yeah, good question. So I also have some other work. If you're interested, feel free to read the paper. And the first one is Agent Coder. I introduced at the beginning that we use different agents to collaborate together to generate code. So we have the code generation agent and also test generation agent and the test execution agent. So now the approach ranks first based on the leaderboard at the Papers with Code platform. You can see that the POSET1 metric is more than 95%. And it has the best results, but with the least token overhead, because with the large language models, we now care a lot about how many tokens you use. And for this approach, actually, it's very sustainable, you could say. So this one is the non-determinism of ChatGPT in code generation. And it's the non-determinism issue of large language models, which means that even if you use identical prompts, you get different results. Yeah, in different machines, and we'll try different times. And so we did a study, and we found that when we use ChatGPT to generate code, the ratio of coding tasks with 0 equal test outputs across 5 requests is like this big, which is very interesting observation, which means that these people try the prompt saying that, oh, large language model is doing great in generating the correct code, but the other person we try with identical prompt may get a completely different code. And this is the frequency of the probability that they get completely different code behaviors. Yeah. So if you're interested in more on large language models for software engineering, and feel free to read our survey. It's collaborated with colleagues from Meta. Yeah. And what else? I think last month I organized the AI-powered software event at King's, and the videos would be online soon. So if you maybe I would probably share it in LinkedIn. So if you're interested, welcome to keep an eye on that. And I'm organizing the AI-Aware conference in Brazil. It's about AI-powered software. So if you're interested, if you go to Brazil at the same time, I guess it's less likely. Welcome to attend. Yeah, that's all. Thank you very much. If you have any questions, any further questions, feel free to ask me.
So I'm going to Brazil 3 days later, actually.
Oh, 3 days later.
It's easy.
How do you go there? Also from Lisbon?
Yeah, Lisbon to Natal.
Yeah.
So sorry.
Go ahead.
I was just looking at your agent code.
Yeah.
You mentioned something about sub-optimization, that you think the model itself to generate the code that you fine-tune on, or what is it?
So we have the test design agent who would design test cases. We have the test execution agent who would run the test cases against the generated code and then provide feedback to the code generation agent. The feedback is the test execution results, for example, which tests are failed.
So you're only updating the context, but not the weights. I understand. You only update the context, but not the weights.
The weights? What do you mean by the weights?
So usually when we fine tune the model, the weights are updated, right?
So that one.
You don't have to do that.
Yeah, with LMs, we just use the LM as the agent. We don't fine tune or produce a new LM. But indeed, it can be interesting to fine tune them also.
No, because just we recently also published this paper today. Actually,
Which one?
it's called.
Is it a similar paper?
It's called Code Optimize.
Yeah.
Self-generated preference data for correctness and efficiency. So basically, we explore how we can use the model itself and generate the preference data that is ranked by correctness and runtime. And then we apply direct preference optimization on it. And we show that not just do we have better correctness, positive, but we also have faster code execution.
Yeah, that's
shorter amount of things.
Yeah.
So I like
Can you send? Yeah, can you send me the?
Yeah. Sorry.
Yeah. Can you send me the paper?
Sure. Yeah.
Is it? It's online, right?
Yeah, it's online. Just here.
You mean my paper or your?
No, sorry, the paper that we did.
You did correct. Because I think we have a similar paper that also recently appeared online. It's also about the efficiency of the code. We produce a benchmark of the efficiency of the code generated by LMs.
What's the name of the paper?
XII bench. Yeah, we can discuss later. I think it's really. So you're from the fourth group?
No, I'm from the
AI.
Yeah.
Right. Yeah.
Slightly more general question about the same thing. So how do you avoid that the test producing agent and the code producing agent kind of mallet up to each other and do something that's actually not the task you wanted to solve?
I'm not sure I understand the question.
So I mean, as I understand it, the one agent is producing code and the other agent is producing tests for it.
Yes.
To test that code.
Yes.
So they could agree through some interaction of the two agents to just produce some completely different code that does something completely different and different tests that then pass that code as being correct, right? So that's what I would call a maladaptation, where you had a certain problem you wanted to solve, but the code generating agent produces something that doesn't solve that problem. Test generating agent produces tests that actually don't test the original problem, but they just pass on what the other guy's producing. So how do you avoid this kind of runaway behavior? How do they get pinned down onto the task they're supposed to solve?
I guess for our situation, we use the GPT-4 and GPT-2.5, and I think they are actually performing very good in code generation and also test case generation. So if the test cases they fail the code, for example, we just produce the fail results to the test generation agent, then our observation is that it could optimize the code based on this observation. And we have in our paper, we have a curve like showing that with the 5 iterations, it actually just keeps increasing within 5 iterations. Yeah, so I'm not sure we observed what you described.
Maybe this says, I don't know whether there is some sort of enough intrinsic knowledge in the LLM that it wouldn't do that, but in principle, you could ask for an algorithm to, let's say, do Fibonacci numbers, right? And it produces some sort of code. And your testing agents makes tests that tests for that. These are actual Fibonacci numbers. and then you have solved it. But you could also decide to make something that's not Fibonacci numbers. If your test agent also agrees with that in a sense and tests for something else as well,
I
you
think
can
I
get
probably
something that's actually not appropriate,
Mm,
and they will still pass the tests and everything. So
yeah, I think I probably let me try to see if I answer your question. So what we did for the test case designer agent is that we don't produce the code to the agent for it to generate test cases because it can be biased by the code. As you said, when the code is not related to the requirement or the prompt, then the test agent might, if we just give the agent the code, then it can be biased by the code. So what we do instead is that we provide the requirements to the agent too, test design agent, so that the test designer agent designs test cases based on the requirement, not the code.
right.
So yeah, so in this way, it's not biased.
And
It's
it doesn't
very,
get any feedback, right? The test designer doesn't get feedback from the code design. So
we,
the other way around.
yeah, we don't, we can't have feedback, indeed.
Okay, I think I understand better now. Yeah.
Yeah, it's quite interesting. We found that even if the code is doing something related to the requirement, but the code is buggy, that would also bias the test case generator.
It would. Okay.
Yeah. I think that's we found that to be really interesting. Yeah, it's like when you, it's like for the developer who writes a buggy code, it's difficult for the developer to detect the bug. So, yeah, so we produce a buggy code to LM, then it's difficult for the LM to produce effective test cases that can detect this bug.
Hey, did you have more questions?
No, I'm good.
You're good? Yeah. Anyone online with questions? Well, Jie? Seem to be. Okay, then thank you so much. It was very interesting. Thank you so much.
Thank you for your time.